Alright, so we're extrusion screw subsystem. Just to go off of the previous group on the auger system, just quickly how that differentiates. Where they're moving material, we're building pressure in order to extrude it. As we've said before, it's been a very daunting task. The non-Newtonian model in which that we went to apply has been very difficult to work with. With that being said, we've moved our phase 2.1 of structures and controls to the next phase, to DR4. We have been primarily concerned about the non-Newtonian model within our extrusion screw in order to build up enough pressure. So, additionally with that, we come into our timeline here. As you can see, we're going to be working to finalize the design and the bill of materials at DR4. We have a tentative bill of materials at the end here that we'll talk about. But like I said, it's mainly non-Newtonian. So we're going to dive right in. While we are using the wet clay material as our working fluid, we instead had to use a different predefined working fluid within SolidWorks called slurry. Slurry is a pulverized solid within water. It's used within the oil and mining industries. So we used that, and then we changed the density within that in order to better reflect wet clay. Additionally, with the viscosity, we used two different models, and you'll see the results on the next slide. The Power Law model and the Herschel-Oakley model. That's just ways that in non-Newtonian fluids you have three separate reasons of viscosity, and that's how it affects the velocity profile of the fluid. As you can see here, the screw builds up enough pressure in the middle and then pushes towards the end. At the very end here, as it comes out the die and it's reaching atmospheric pressure, it reduces its pressure nearly to atmospheric, and that's what drives the extrusion process. The reason why you wouldn't see that as a higher pressure is because the diameter of our barrel, which is what is around the extrusion screw, is not significantly larger than the area that we are extruding out of. So we have a 12-inch barrel where the extrusion is 4x10. So you would think that this would be a high pressure and this stuff would just be shooting out like a water gun. Instead, it's going to be a little bit slower, and that pressure is going to change just before it comes out the die. So as we went through our report last time, our horsepower was about 8.68, and so we're using that as our minimum steady state. So if everything's going well and good, that's what we're going to have going. We want to have a transient available horsepower of 9, and so that's just to get it up to speed. That if there is clay being put into the extrusion screw, into the hopper, we can get up to speed. And then 10, we want to be our max horsepower, in seeing that if there is a larger solid in there, if it didn't get broken up, it can hopefully push that through. Finally, on the two models down here with RPM and torque, these have been the hardest numbers to get with the non-Newtonian model. So on the left here with 32 RPMs, that's the Power Law model that we use, and the 210 feet-pounds, foot-pounds, those are also the Power Law. And so it seems that there's no quite convergence between the Power Law model and the Herschel-Buckley model and the additional preliminary model that we made, just using a solid. We're continuing to work with that. We see a maximum of 210 foot-pounds there. So that's what we're going to work with. We're not going to try to get too detailed because we got to keep moving. Additionally, there's our RPM. What we did here primarily, and I know y'all can't quite read this, but the three most important is two processes that happen with the auger and one with the housing. The main concerns with the auger is that we don't want it to deteriorate. We want it to be accessible to maintain. If the auger fails, it's two areas, which is either on the disc, which is the thing that has the flight angle, or the shaft. The entire machine has to come to a standstill and production stops. So those are our primary concerns with the auger. The way that we address that is we look at material that is corrosion resistant, and we have thick enough material so that it can withstand quite a bit of cyclical stress and maximum stress. Finally, on our housing, because we are pressurizing, we want to make sure that our housing has adequate hoop stress within the thickness of the barrel, as I was calling it earlier, to make sure that it doesn't crack, because if that cracks, then the whole machine has to be disassembled and reassembled completely new barrel, taking time and money. So those are our three that we are working towards to address. Additionally, we have our I'm back here. in order for it to explode, we're going to have, we call this end support here, and we'll have a bearing attached. We have that bolted outside of the barrel, and so you remove those bolts along with the die, and then you remove the auger all the way out. So on the back side, there would be another bearing that you could slide it into. The way we want to do this in the front is because we know the power team is going to have the gearbox and the motor on the back there, and we want to make sure that we weren't messing with their stuff, that when they can just keep that and we can pull it out the other way. Additionally, you'll have the rollers here, so you can easily pull the auger out, and you don't have to have too many people there, and it's not as dangerous. A quick note on the die, I know the die team is using a different way to fasten the die here. Instead, we use bolts just to keep it simpler and so our model can run smoother. Finally, come to our last slide is our tentative bill of materials, which will be more detailed in the next DR4. And so, obviously, we're going to need steel roller bearings, the conveyor auger. The way that we're saying that is we need to figure out if we're going to have a custom auger or if we're going to purchase one. That's just the way that we're going to need to machine that, figure out if it needs to be transported, and that'll work into the cost. Additionally, we're going with the 12-inch steel pipe, or barrel as I was calling it, bolts to secure the support, and the steel plate, which is what the end support will be machined out of. The studies that we need to determine those three the specifications on these three parts, we need to determine plate thickness, the specifications for the bolt, and the thickness of the steel plate. These are governed by different theories or stresses, I guess you could say. Obviously, the barrel is hoop stress, like I said earlier, shear force on the bolts so that we have the linear force coming from the clay and the auger, and then the steel plate as the end support. We make sure that it can last long enough with having that pressure coming forward. So, that is the end of our DR3 discussion. Any questions? Yeah, so the back side of that hopper will have a static bearing. So both, yeah, and those are just going to be welded on there. So that if you do have to service the bearing, you're just going to have a whole different end support there. Yeah, and so because you guys are power requirement, right? Yeah. Yeah, so we just wanted to make sure that that shaft's just going to come out a certain way, attach it to whatever gearbox you all need or whatever belt you all need, and it can come right out so you don't have to worry about moving anything, any levers there. Any other questions? Perfect.
Thank you.